I'm sure some of you have heard of the Andes Mountains of South America. This is a region of the world with extreme climate where people have still succeeded in growing bountiful crops of corn, of soybean, just about every vegetable imaginable. And this becomes even more incredible once we realize that these regions have very low amounts of water and weird temperature effects which make them very unsuitable for growing vegetation. So how are these people able to achieve these yields of crops in such a hostile region? The behavior of water is going to give us a key insight into why this is possible, and this is the question that we will explore towards the end of this lesson based on what we have learned. So, whenever we are supplying heat to any material, so let's say that I have a given mass of material. It can be anything. It can be a block of aluminum, it can be a bucket of water, it could be a balloon filled with air. But we have a particular material, some kind of matter, and I am supplying heat energy to this mass through some means. I could be using conduction or convection or radiation. The question is, what will be the change in temperature for this particular amount of substance if this much heat energy is applied to it? If we look at this qualitatively, we will notice that different materials will change their temperature by different extents for the same amount of heat input, even if their masses are the same. Quantitatively, we can look at this as a ratio between two quantities, the amount of heat gained or lost by a material and the temperature increase or decrease in the material due to this gain or loss respectively. So we can define a quantity, let's call this quantity S, capital S, which can be equated to delta Q by delta T, where delta Q is the change in the amount of heat energy that has been supplied to this substance or the heat energy extracted from the substance, and delta T is the change in temperature caused by the addition or the removal of heat energy from this substance. So this quantity, capital S, we can define as the specific heat for this particular material. So can we refine this quantity specific heat further? Can we define it for the unit mass of a substance? So what we have here, capital S is equal to delta Q by delta T, is for any given mass of material. So obviously, if you had 10 liters of milk and you had 2 liters of milk, the addition of the same amount of heat energy would change their temperatures by different amounts because the masses of these two amounts of milk would be very different. So we need to refine this value of specific heat in such a way that we can define it for a unit mass. We can do this by creating another quantity, that is small s, and this quantity can be defined as capital S divided by m. So this is the specific heat for a unit mass of this particular material, for a kilogram of this particular material. We can refine this value of specific heat even more by thinking in terms of moles rather than in terms of kilograms. So we can define yet another value that is denoted by capital C, and this is what we call the molar specific heat for a given material, and this can be found as capital C is equal to capital S divided by mu. So this becomes equal to 1 upon mu times delta Q divided by delta T. So here mu is the number of moles of a particular substance. Now the number of moles is a concept which is true for all materials equally. So this is very useful to us in understanding how same masses or same amounts of different materials will react for a given amount of heat energy put into them or removed from them. Different materials have different values for S, C and capital S. We have to also understand that in terms of gases, the calculations become a little more complex because gases can have widely variable volumes and pressures. So for gases, we can define this quantity in two different ways. So we can define two different specific heats for gases. These are Cp and Cv, where Cp is the specific heat for the gas which has been calculated at constant pressure. If you remember, if we apply heat to a gas at constant pressure, there will be a change in its volume. So that change in volume or the constant pressure is accounted for in the calculation of the specific heat or the molar specific heat of a gas at constant pressure. On the other hand, we can also calculate this value for constant volume. So we have Cv, that is the molar specific heat for the gas at constant volume. We will understand and work with these two values in more detail in later sessions. Now, coming back to the original question, why were the Andeans able to grow these crops even though they are dealing with a high altitude region where it gets very cold and there is not enough water? What they use is a technique called trench irrigation. What they have done is they create parallel trenches inside the ground which they will fill with limited amounts of water. Now, water is a very interesting substance because it has an anomalously high value of specific heat. To put that in perspective, if you look at lead, which is the densest material among normal common day materials, it's a very dense metal, actually has a rather low value of specific heat. For lead, it is only about 127 joules per mole per Kelvin. Aluminum is higher at approximately 900 joules per mole per Kelvin, but water, which is a compound which has much lower molecular weight compared to either aluminum or lead, has an anomalously high value of specific heat. It is 4186 joules per Kelvin per mole. And because of this anomalously high value of specific heat, water is a material that can absorb a large amount of heat and release a large amount of heat without much change in temperature. Now, the Andeans did not know about this. What they realized, however, was that if you were to fill these trenches with water, and if you were to grow the vegetables between these trenches filled with water, what would happen was that in the bright morning sunlight, the water would be able to absorb a large amount of thermal energy without much change in its temperature. So the water would be able to increase its temperature by gaining a huge amount of heat, but because the temperature increase was not very great, the plants would not be badly affected. Now, the problem with growing stuff in the Andes is that the night temperatures can become very low, and this can cause something that we call frost. Frost is extremely bad, very dangerous for plant life. It can easily kill any plant that is exposed to it. But the beauty of this irrigation system is because the water has absorbed so much thermal energy in the morning, at night it will start releasing this thermal energy into the plants, into the field where this water is stored in these trenches. And because of this, the temperature of these plants will never drop low enough for frost to form, and this protects these plants from frost damage and ensures great yields of vegetables all year round. So this is a very interesting example of how folk wisdom can combine with scientific understanding to create solutions where no solutions seem possible.
Manorama Horizon, learning made simple.